So for a diesel cycle, the four processes that happen are kind of similar. The main difference is in the way heat is being added. Okay, so you have an isentropic compression just like we had for an Otto cycle. And then you have a heat addition process. In the Otto cycle, it was constant volume, but here we are having a constant pressure heat addition. And then you have an expansion, which happens during a part of the power stroke. And then 4 to 1 is the heat rejection, the constant volume heat rejection. The heat rejection is always constant volume in all the different cycles, dual cycle, diesel cycle, Otto cycle. The heat volume, the heat rejection always happens at constant volume. The only difference is the way heat addition occurs. Now, for an Otto cycle, we had heat addition occurring at constant volume, but here we have it occurring at constant pressure. The reason why we have it occurring at constant pressure is simply because this is more representative, or it resembles what happens in the actual cycle, in the actual diesel engine. So let's look a little bit into why that is happening. Okay, why do we have constant volume in Otto cycle, and why do we have constant pressure here? So if you look at the older diesel engines, right, the earlier diesel engines, what we would do was we would compress the air, right, and as the air gets compressed, it goes to high temperature and pressure, and the piston reaches the top dead center, right? When it's at the top dead center, at the end of the compression stroke, that's when we would inject the fuel. So as you know, once we inject the fuel, the pressure and temperature of the fuel air mixture is so high that the fuel will ignite. The fuel air mixture will ignite immediately, and as it ignites, uh, it's going to push the piston down. But the piston is already in the expansion stroke or the power stroke, so it is already starting to go down as the ignition happens. So as the ignition happens, we are going to have the piston is already moving, so the pressure remains to uh, remains more or less constant. So it's you can think of it as some sort of a free moving piston. Okay, you're adding heat, of course, but the volume is also increasing. The piston is already going down by itself because it's already in the power stroke. So as we keep on adding heat, the piston is going down, the volume is increasing, and therefore the heat addition that happens in a diesel engine, it resembles a constant pressure process, and that's the reason why we have heat addition at constant pressure, right? So this is the main difference between a petrol and a diesel engine, or gasoline and a diesel engine. Now, certainly, since we are having heat addition at constant pressure, we know that when we are adding heat at constant pressure in a free moving piston sort of assembly, boundary work is being done as the piston moves down, right? So there is some work output that's happening during the heating process as well. So the diesel cycle therefore has a two-step power stroke. Uh, a power stroke during the process 2 to 3, meaning some work done during the heat addition process, and also the work done during the actual expansion process from 3 to 4. Okay, so this is what mainly happens in a diesel engine. Before we go forward, any questions here? Anything that's not so clear?
Doctor,
Yes.
can you hear me, Doctor?
Yeah, I can hear you.
Doctor, where is the heat source in the diesel engine? I didn't get idea of.
Okay. Okay, that's a good question. So in a diesel engine, well, the heat source is basically combustion, right? Burning of fuel is what provides us all the heat that pushes the piston down and does the work. Now, in a diesel engine, uh, we compress the air, and at the end of the compression stroke, when the piston is near the top dead center, right, somewhere here, that's when you inject the fuel. So the fuel, when it's injected, it mixes with air and immediately starts to burn. So that's when the heat addition is happening. So the fuel starts to burn and the piston is already moving down as it's already at the top dead center. So as the fuel burns and provides a lot of heat, the piston is also moving down. So the pressure does not rise up, but pressure remains more or less constant because the volume is increasing as the temperature is increasing. So that's where the heat addition happens.
So, Doctor, can we make like this idea by using a benzene as a fuel source instead of diesel?
Okay, that's a good question. So, well, in this sort of like if you heat up the fuel and if you heat up the air and then inject benzene, I mean the correct name is gasoline, right? So if you inject gasoline, its properties are different. So not all of it will burn immediately. It will take more time to burn. And since in an engine we are operating at like say 1000 RPM at a minimum, or let's say 800 RPM at a minimum, we are having all these processes in the happening in the order of few milliseconds. So we need a fuel which is very reactive. Okay, so gasoline is not gasoline, or as you guys say benzene here, it's not very reactive. Uh, Diesel fuel is more reactive. So it is about selecting the correct chemical or the correct fuel. You want so you want the ignition to happen immediately when you inject the fuel here. So that's the reason why we make of diesel. We make use of diesel. Gasoline will not do the same job. It may or it may not ignite completely, uh, and well, if you put a gasoline in a diesel engine or a diesel car, you will also have problems with the fuel injector because the gasoline is less viscous. It'll not lubricate the fuel injector properly. There are tons of other issues, but yes, in terms of combustion or other stuff, it will not ignite. It may not ignite completely or immediately. Does that answer your question?
Yes, yes, thank you.
All right. Any other questions? Okay, so then let's move forward and let's do an energy balance for this. Okay, so now let's focus on the process 2 to 3, which is the heat addition process. Now we said this sort of resembles what's happening in a free moving piston. So as we are adding heat, the piston is moving down, right? So there's some heat input coming, but as the piston is moving down, it's also doing some boundary work. So as we discussed before, the energy uh, transfer that's happening within the piston cylinder assembly is basically the energy transfer in a closed system. So in a closed system, there is the only way in which energy can get transferred is through heat and work. There is no mass transfers involved, right? So the uh, the 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 energy transfer is basically going to be equal to the change in the internal energy of the system. All right, since we are dealing with a closed system. So here, as we said, for a free moving piston, okay, as we are adding heat, some amount of work is happening, and we need to write down how much work is happening. But the thing is, the key point is that the pressure is remaining constant. So what I could do is I could just write Qn, some amount of heat that I'm adding. I can send the boundary work to the other side. So I could write it as U3 minus U2 plus the boundary work. Now, for a closed system, the work done is integral PdV, right? But here, since we are going from process 2 to 3, which is a constant pressure process, I can remove P outside the integral, and what I have is simply V3 minus V2. And if I want to write in terms of specific work output, right, small w, or work done per unit mass, it'll be pressure times the difference in the specific volumes, V3 small v3 minus small v2. Okay, so this is what I have. Now I can use this formula of work output along with the internal energies and come up with another expression. So here, when I send the work output to the other side plus the internal energy difference, this is what I'm gonna get. Okay, so if you look at this, this can be written as U3 plus P3 V3, and I'm able to write P3 here simply because P2 is equal to P3, right? The pressure is exactly the same from 2 to 3. Okay, so this is one part where I'm taking these two things minus U2, what is this part right here, plus P2 V2. Okay, so again, I'm able to write P2 here because P2 is same as P3. It doesn't really matter. I can write P2 there, I can write P3 there. Now, the reason I've written it here in this format is because I want to make use of the definition of enthalpy, right? So we know that H is equal to U plus PV. So U3 plus P3 V3 is nothing but enthalpy at state 3. Its value is the same, right? Same way, U2 plus P2 V2 is H2. So what I could do is from energy balance, I could basically equate Qn to H3 minus H2. Okay, and this is what happens here. So Qn for a constant pressure process is equal to H3 minus H2 when you're doing the process from 2 to 3. Now, if you're treating the air as an ideal gas with constant specific heat, then you can write this delta H as Cp delta T. Okay, so this is an assumption. This will only hold true if the question mentions that you can treat air, you're considering cold air standard assumptions, or if you are considering the air to have constant specific heat. If nothing is mentioned about constant specific heat, if nothing is mentioned about specific heat, you just need to go ahead and make use of this the correct formula, or you have to make use of the enthalpies, right? You cannot make any approximation. So this is the main difference that comes in. The heat addition process is different here. The heat rejection process is exactly the same. You still have a constant volume heat rejection, and it's simply going to be U4 minus U1, just like we discussed before. And if you're not having variable specific heat for an approximation, you can always treat it as Cv delta T. Of course, when the question mentions that you can go ahead with the approximation. Okay, so this is what we have in terms of Qn and Qout. The main difference is in terms of Qn, right? Qout is obviously the same. So we can go ahead and write the thermal efficiency of a diesel engine, because all we are looking for is to figure out what are the different things that affect the efficiency of a diesel engine and to figure out a way to improve them. So the efficiency of a diesel engine is simply net work out by the heat input into the cycle, or 1 minus Q out by Qn. We have the formulas for Q out and Qn from the energy balance. So you can just write that as 1 minus U4 minus U1 by S3 minus S2. Now this is the general formula, okay, and this is always true. We can certainly simplify it and write it in terms of temperature differences if the question mentions about constant specific heats. Of course, this will become more clear when we solve the problem, which we will be doing it in the next class. Okay, so if the question mentions that you can consider cold air standard assumptions, which basically tells you that air is an ideal gas with constant specific heats at 300, evaluated at 300 K. So in such cases, I could just write the efficiency as 1 minus Cv times T4 minus T1 divided by Cp here, because I'm having enthalpy, Cp times T3 minus T2. Now, when we were dealing with the Otto cycle, we could just cancel out the specific heats and go ahead. But here we don't have the same specific heats. We have Cv at the top for delta U, and we have Cp at the bottom for delta H. So here, I'm not going to cancel them out, but I'm going to replace it with the ratio, with a specific heat ratio, Cp by Cv. And as we saw in the last class, this specific heat ratio is a property of the working fluid. It varies from one fluid to the other. It's different for air, it's different for argon, and so on. All right. So once you have that, then you can write it as 1 minus T4 by 1 minus T4 minus T1 by K times T3 minus T2, right? And of course, we can go ahead and do some manipulation to come up with a simpler version of it, simpler version of the thermal efficiency. Okay, in terms of compression ratio, in terms of the parameters which are typically provided by the engine manufacturers. Now, before we go ahead and talk about that other formulation, other simplification for thermal efficiency, I also want to define one more parameter. Now, for diesel cycle, for Otto cycle, we already know the compression ratio, right? The compression ratio is simply a ratio of maximum volume to the minimum volume within a cylinder. So here the maximum volume is going to be V1 again. The minimum volume is again going to be V2, or the volume at state 2. So it's basically the volume at the beginning of the compression process and volume at the end of the compression process. However, because we are having heat addition at a constant pressure, during the heat addition process also the volume increases, right? V3 is going to be greater than V2, of course, because as we are adding heat, the piston is moving up, moving outward, moving downward, and therefore some boundary work is being done. Okay, so since V3 is always greater than V2, we would want to quantify how much it is greater, and therefore we come up with this ratio called the cutoff ratio, RC, denoted by RC, which is V3 by V2. This always is going to be greater than 1, simply because V3 is greater than V2, as far as we're looking at a Diesel cycle. Now, if you want to write the thermal efficiency formula for a Diesel cycle in terms of R, the compression ratio, and RC, the cutoff ratio, this is how it's going to look like. Okay, so how did we come up with this expression? Well, we just made some simplifications and made use of um, the formula relating temperatures to specific volumes for isentropic processes, and that's how we came up with this expression. So what's with this expression? What all is happening in there, right? What are how is the thermal efficiency going to vary with compression ratio? How is it going to vary with cutoff ratio? We'll see that in the next slide. So before I go ahead, any questions here? Okay, looks like everything's clear. So everyone is going to get full marks in the first try in pop quiz then. So let's go ahead. Okay, so let's again look at this formula. Okay, this is the formula that we just had, the thermal efficiency of the Diesel cycle, right? So this is the formula we had, 1 minus 1 by R, K minus 1, times some part related to the cutoff ratio. Sorry. So let's first look at the compression ratio. Okay, let's see what's going to happen with increase in the compression ratio. So as we so this plot here shows the thermal efficiency of the Diesel cycle on the y-axis and compression ratio on the x-axis. As we keep on increasing the compression ratio, what we see is that the thermal efficiency increases, right? And this is exactly same as what we saw even for the Otto cycle. And this is pretty obvious why that's happening, right? So if you go back to the this PV diagram here, or the TS diagram, as we increase the compression ratio, what we are essentially doing is we're increasing the value of P2, right? The P2 is going to increase, T2 is also going to increase. So as the pressure increases, the temperature obviously is going to increase along with it. And once you increase T2, what you're essentially doing is, since we are adding heat between process 2 to 3, so increase of T2 simply means that we are increasing the temperature of heat addition, right? We're simply increasing the temperature of heat addition. And when you increase the temperature of heat addition, the thermal efficiency simply goes up. Okay, so you can again relate it to the Carnot cycle, 1 minus Tc by Th. By increasing the pressure, what we are simply doing is we are increasing the Th. Okay, so if you increase Th, of course, the thermal efficiency would go up. Now, of course, here we are dealing with a Diesel cycle, not with the Carnot cycle. So the amount by which it goes up would be different, but essentially is the same idea, right? So if you increase the temperature of heat addition, no matter what cycle you're dealing with, the efficiency would certainly go up.